Alright guys, today we're going to talk about bisectors and triangles, a few of the theorems that go along with them. We've already talked about bisectors as far as angle bisectors and perpendicular bisectors or segment bisectors as well. So we'll just look at their relationships in triangles and their relationships to segments. Okay, so we'll go through a couple of these theorems and then I'll try to explain why they work that way, and that will be this notes section. Okay, so we're going to talk about two basic theorems, and it's the perpendicular bisector theorem, written right here. If a point is on the perpendicular bisector of a segment, then it will be equidistant from the endpoints of the segment. Okay, so that's enough to say, but I just want to show why it works that way. Okay, so here we have CD as a perpendicular bisector. You can tell it's a bisector because AD is congruent to DB. You can tell it's perpendicular because it's 90 degrees here. It's a perpendicular bisector. Okay, this theorem says that this point should be equidistant of the midpoints of the segment it bisects. It bisects AB. Okay. What we're going to do is we're going to use our triangle congruencies to prove that CB has to be equal to AC. Okay, so they already told us that AD was congruent to each other, or AD and DB were congruent to each other. They also told us that these are 90-degree angles. Okay, now the thing that we can use for ourselves is that we can see that CD should be equal to itself because of the reflexive property. And so we have that these two triangles should be congruent by side, angle, side. Okay, since they're congruent by side, angle, side, we know that CB should be congruent to CA by CP, CTC. So would AC be congruent to BC? Yes, every single time. Okay, this next point just shows that it's not just because C is in a specific spot. If we made a new point, let's call it E. We put it anywhere, E1, E2, it doesn't matter. No matter where we put it, this side would be shared by the reflexive property. So anywhere up and down this line, anywhere on the perpendicular bisector, it would be equidistant from A and B, the endpoints of that segment. Okay, the converse just says it the other way. If we know that this point is equidistant from the endpoints of a segment, then it has to be on the perpendicular bisector. Okay, and so we see that CB and CA are equal to each other. C is equidistant from A and B. So what do we know? We know C is on the perpendicular bisector. Okay, so this perpendicular bisector is in this theorem. Now the angle bisector theorem says that if a point is on the angle bisector, the bisector of an angle, then the point is equidistant from the sides. One thing that we have to make sure that we know is that equidistant, when we talked about a point to point, it's just a straight line. But when we talk from point to line, it's a straight line, but it's perpendicular. It's a perpendicular distance. Okay. And so X is on the angle bisector. We'll draw that in. Okay. This perpendicular distance then, since X is on the angle bisector, X will be, or XC will be the same as XB, the congruent. Okay. And the converse just says if the point's equidistant from the sides of the angle, then we know it's on the angle bisector. Okay. Now let's look at an example for this. So let's just give this some value. So let's say that this is 5x, and this is 3x plus 24. Okay. If this is on the angle bisector, then we would be able to say 5x equals 3x plus 24. Okay. From there, we would solve for x. 2x would equal 24, x would equal 12. Okay, because this x is on the angle bisector, we know it has to be equidistant and equal perpendicular distance from the sides. And so we could tell that the distance from C to this x would be 60, 5 times 12, and the distance from x to B should be the same, 36 plus 24, 60. Okay? Alright, short and sweet, bisectors and triangles.